Hello everyone, welcome back to my live stream. So yesterday we were solving the coding questions that appeared most frequently in Apple interviews, and let's keep continue with that. Let's keep going with that. We had solved 8 out of the 12 most frequently appeared problems in the last 30 days. Let's first try to complete the let's first try to complete this list. We have 4 more problems that we need to complete. After that, let's see um, if we need to extend our time duration to 3 months, or if we get into solving some other company specific problems, we can decide that. Let's look into let's try focusing on finishing the remaining list as now. So here, longest substring without repeating characters. I don't recall uh, solving that. Okay, given a string s, find the length of the longest substring without duplicate characters. And the string is given as, okay, I think we had seen this one, ABC, ABC. So we were kind of using a sliding window concept, and for keeping the current window, we used a hash set, and then we were adding the new letter that we are iterate, and we start iterating from 0, and then we kept adding the new letters that comes, or new characters that we come across into the sliding window. And then here we are checking if the sliding window already contains that character. Then what we did was uh, we kind of what do you call, we contracted, or we reduce the window like from the beginning until we find that until we make sure that window doesn't have any duplicates. So the basic thing is we are considering the window which doesn't have any duplicate character, which has all the distinct character. For example, let's consider this example. So we started iterating. We have basically two indexes that we are, two pointers that we are using to signify the start of the sliding window and then the end of the sliding window. This is the end of the sliding window, whatever we are using here as I, and start starts with 0 as well, and end starts with 0 as well. So now like we came across the first letter A. So A is not in the current window. Already current window is just nothing, or an empty string, or of 0 characters. So we added that character A into the current window, and then the max length until now is 1. And then we looked into B. B is not in the sliding window, so we added that character also to the current window, and the max window became 2. And we came across C. We added that to the window, and max length became 3. And then we came across A. We checked that, okay, that was already present in the window. So here we have been checking, while current window dot contains s dot caret I. Yes, it contains. So we have to we what we do is we will remove the character that is pointed by the start of the window, and we will increment the start. Okay, luckily here the first, after removing the first character itself, which the start was pointing to, all the other characters were distinct in that window, BCA. And then we start with the B, but again B was contained in the window, so we need to remove remove B from the current window, and then increment it the start to point to the next character as well. And then okay, we again got kind of distinct characters window CAB, but when we try to iterate the next window C, again we found the duplicate, and then we had to increment the start by 1, and then we found another window ABC. So now in the next character, like, okay, we came across B. So in ABC, B is we have B, but before removing B, we are shrinking the sliding window or the current window. So we need to remove A first. Start was pointing to A, so we removed A from the window, and then but still the condition didn't satisfy. The next character is still in that set, or the current window set. So we checked and we removed this one also. At that point, okay, we ended up shrinking our window to have only B. After that, we added the next B, but then we checked again the next character B. So next character B is also correct contained in the window. So we had to remove C and remove B, and then our current window just contains B. So we never got a chance to update our window size to greater than 3 size after like initial window, like whatever we got here 3, that's the max window length. So we stuck to that one. Wish we had looked into some other example. We will come across some other scenario. Just understand the concept, and we I think the implementation is fairly straightforward here. We have the current window, and here we are iterating through the array in this for loop, and then if we are checking here if the current window already contains the character that we are trying to iterate through. If it already contains, then we need to keep removing the character from the current window until we satisfy that all the characters in the window are distinct, and then we incremented the start index as well. After we made sure that all the characters in the window will be unique, we added that next character to the current window, and then we checked if the current window length is greater than whatever the past window length, and then we update the max length. After iterating through all the characters, we are just returning the max length here. So that should be it about this LeetCode 3 longest substring without repeating characters. Let's move on to the next problem now. Find median from data stream. So LeetCode 295, find median from data stream. This is marked as a LeetCode hard problem. The problem states that the median is the middle value in an ordered integer list. Okay, they have provided the definition of median. Median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of two middle values. For example, 2, 3, 4. This is the odd length sequence or odd length array in this, and it is sorted as well. In this one, the median will be just 3. And then if this is the even length array, the median will be 2 plus 3 divided by 2. You see that would return 2.5. So implement the median finder class. This is a constructor which will initialize the median finder object, and then add num. They are adding an integer by taking it as a parameter. Adds the integer num from the data stream to the data structure, and double find median. Find median returns the median of all the elements so far. Answer within 10 power minus 5 of actual answer will be accepted. Answers within 10 power minus 5 of the actual answer will be accepted. I did not understand this one. Answers within 10 power minus 5 of the actual answers. Okay, see, so this is like they are talking about the accuracy of the answers. So we are this should be in the double format. So whatever the parameter that we are adding here, that is in the integer format, but whatever we are returning here, so that is in the double format. So we should perform division in terms of like double or floating point double division there. So let's see how we can solve this one. So here the problem is, as the stream of data is coming in, like in this method, like whenever we need to add the number, so those numbers are not in the sorted order. So it's not given that the numbers that would be coming into that method, that we would be getting in this method, isn't guaranteed to be in the sorted order. So what we need is basically kind of a data structures which would help keep the elements in the sorted order. And also another thing that we notice is, okay, what all data structures can help us keep something in the sorted order. So we come across a couple of things like tree set or a tree map, which would maintain the sorted order, or which would make it easy to retrieve any elements in the sorted order here. And another thing is heap can continuously return the minimum or maximum element from the data structure, and we can find all the elements in the sorted order in n log n time, so better than n square. So yeah, so that is as good as getting the elements and then sorting it, but this would maintain it in the sorted order. So the find median will be much more performant. What other things, what other traits that we can notice here? Here, all we care about is the middle element or the middle two elements. We don't care about the other elements, whether they are in the sorted order or not. We do not care much about it. So that would be the key point in formulating the solutions. Here we are using two priority queues in order to come up with the solution. Two priority queues. Let me explain why two priority queues. So both the priority queues, like one priority queue would keep the first half of the list, I mean in the first half of the sorted list, and other priority queue should contain the second half of the sorted list. So for example, if 2, 3, if this one was given, the first half of the priority queue should have contained 3, 2, and the second half of the priority queue should have contained 3. And if this problem was given, either 2, 3 was contained, I mean, we can make sure which part contains the additional integer here. So let's assume, okay, 2, 3 would be contained in the first half of the priority queue, and 4 would be contained in the second half priority queue. Okay, I'm doing the same thing. I'm initializing two priority queue, first half max priority queue or max heap, and second half min heap. Okay, two priority queues, first half max heap and second half min heap. So since first half max heap, like by default in Java, heap or priority queue are min heaps. So in order to make sure that it's a max heap, I'm sorting it in the reverse order. Like we need to pass a sorting function uh, or an implementation of a comparable interface. So I'm just passing collections.reverse order into this into the constructor of priority queue, which would make sure that it is sorted in the reverse order in the priority queue. So first half max heap and then second half min heap. Why exactly first half max heap and second half min heap? Because I think I was talking about that logic that we are going to follow. So here, if let's say there are, instead of these two elements, let's take an example of, like, okay, let's take this example. Let me have a little bit of 7, 7, 4, 5, 1, 6. Okay, let's say our data stream is coming in this order. If this is the case, first half min heap, sorry, first half max heap should look like something like this, and then second half min heap should look like something like this. So what am I doing here? First, add number. In the add number, all I'm doing is, let's trace whatever we had doing with this example. Okay, add number 2, let's say second half min heap dot offer. I'm adding it to the second half min heap. So second half min heap, okay, 2 came in, I just added it to second half min heap, and then I'm removing it from the second half min heap, removing one of the elements. I mean, not exactly whatever, not exactly the 2, but removing whatever is the min element in this second half min heap, and then adding it to the first half max heap. So I am polling this element and then adding it to the first half max heap. Okay, and then if first half max heap dot size greater than second half min heap dot size, then I'm just again adding it to the second half min heap by polling it from the first half max heap. So yeah, this looks like a futile thing. Basically, I'm kind of removing it from one priority queue and then adding it back in another priority queue here. But trust me, it will be useful in the next steps when I'm adding additional elements in from the data stream. Let's perform the same thing here. Okay, now 3. I need to add 3. So what I'm adding is what I'm doing is second half min heap. I'm adding it to the second half min heap. So in second half min heap, since it is a min heap, so it will be, so min will be at the top anyway. Min element will be at the top. So 3 will be added next to that. And then first half max heap dot offer, second half min heap dot poll. When I do second half min heap dot poll, now 3 won't be removed, but the minimum element from the second half will be removed, which is 2. And then I'm adding it to the first half max heap. So this is removed from here, 2 is removed from here, and then will be added to the first half max heap. And then here I'm checking if first half max heap dot size is greater than second half min heap. It this doesn't satisfy. This is not true now. So we won't do anything. So 2 came here and 3 came here. Let's assume that, okay, at this point, if someone wants to check the median value, okay, if someone wants to check the median value, find median, then what we are doing is, if second half dot size is greater than first half max heap size, then we are just returning the peak element. In this case, both the sizes are similar. So what we are doing is, we are taking the peak element from both of those, second half min heap dot peak and first half min max heap dot peak, and then dividing by 2. So both the peak would return 2 and 3. So 2 plus 3 divided by 2, it would return 2.5. So this would work as it is. Let's see here. Let me have 4 and then 7. Okay, let's follow this order instead of that. Okay, now in this case now I'll be adding 4. So when I want to add 4, second half min heap dot offer 4. So I'm adding 4 to this min heap, and then first half max heap dot offer, second half min heap dot poll. So when I poll second half min heap, I'll remove 3. I'll get 3. I'm removing it from here, and then I need to add it to the first half max heap. Since first half is max heap, 3 will come at the top here. 3 will be at the top, so I'm adding 3 here. And then here I'm checking if first half max heap dot size is greater than second half min heap dot size. I'm adding it back to the max, adding it back to the removing from the first half max heap. So when I remove from the first half max heap, the maximum element is 3, that would be removed, and that would be added to the min heap here. So min heap means 3 would be at the top again. So that is done. So at this point, let's say if someone is asking for a find median, then what I'm doing is, if second half min heap dot size is greater than first half max heap dot size, which is true here in this case, second half size is greater than first half size. So what I'm doing is, I'm just returning the peak element from the second half. Peak element from the second half is 3. I will just return 3, which is the expected answer here. If array contains only 2, 3, 4 and we need to find the median, so this is returning 3. So here in this case, I'm adding it in the order 2, 3, 4. But even if we added it in the order 4, 3, 2, 3, 2, 4 or anything, that would have returned 3 as the median, because we are that is getting arranged in that order using these 2 priority queue schemes. So next, let's say let's keep making it, keep adding the elements. So now we need to add 5 here. So 5, how we will add? First thing is, we need to add it to the second half min heap. So when we add 7 to the second half min heap, so that will be added here, let's assume. And then okay, and then we need to, we are checking that, and then we need to remove one element from the second half min heap and then add it to the first half max heap. So let's do that. When we remove it, the minimum element will be removed, and then we are adding it to the max heap, and that will be at the top. So 2, 3, 4, 7, it will be like this. And then we check that the size is not greater than this, sizes are equal, so we won't do anything. So next step is 5. We need to add 5. So we will be adding it to the second half min heap, and then we will remove the first element from the second half min heap and add it to the first half max heap. So we removed 4, and then we will be adding it to the max heap, so that will be at the top. And then next thing is, basically again we are checking if the first half size is greater than second half, then we will have to remove 4 from the second half and then add it to the first half. So we removed 4 from here, and then we added it here into the min heap. That would be the top element here. So until here, it's kind of as expected. So we added 7. We are done with adding 7. So let's, sorry, we are done with adding 5. So let's move on to add 1 now. Now this, like whatever I'm doing, like back and forth, it makes sense. So here, now I need to add 1. What I'll do is adding 1, that would be like, I'll be adding it to the second half min heap. So that would be at the top. But when I try to remove it, when I try to poll from the second half min heap and then add it to the first half max heap, so I will be polling the min element here, so that would poll the 1, and then I'm adding it to the first half max heap, so that would be, but that would go to the bottom of the first half max heap, and max element will still remain as 3. And then next, when I'm adding 6 here, so 6 won't be the top element here because this is a min heap. When I'm adding the 6, when I'm adding 6, 6 would be somewhere here, 6 would somewhere here, sit somewhere here, and then I will be removing one element, but 6 won't be removed at this point. It will remove the min element from the second min heap, second half min heap. So I remove 4, and then I'll be adding it to the first half max heap. But when I compare the max heap, the 4, whatever I removed from there, that would be the top element here. And then now I'm checking the size of this one. So 4 is the greatest element here. So I'm pulling it from this one and then adding it back to the min heap here. So the order is preserved. At this point, if someone checks the median element 1, 2, 3, and 4, 5, 6, 7, so now the second half min heap size is greater than first half max heap. So I'll be just returning the peak element of the second half min heap, which is 4. 4 would be the median, so which is the correct answer. So keeping it this way, like keeping all the elements of the first half in the in a first half max heap, and all the elements of the second half in a second half min heap, we will have direct access to that middle element, like in order to determine the median value. And we do not care other elements are sorted or not. A heap doesn't promise the other elements to be in the sorted order, but it promises that the top elements will be either min in the min heap or max in the max heap. So yeah, through which we will get the median value on the run here. And the complexity of this add number is log n, where n is the number of the elements that is already contained in the heap. So it will take log n to heapify operation in both of these heaps. And then here for find median, we are doing it in constant time. Like we are just getting the peak element and then we are returning the value by computing it. So this would be a constant time operation. That should be about it. Let's submit it and see. Okay, so this one works. Okay, and let's check the answer if there is any way that we can optimize this one. Okay, 2 heaps approach. Okay, here in this implementation, they are just adding the extra element to the second half. So basically, kind of using the second half element, like we are using the second half element to keep the extra element, like when like for example here, when there is an additional entry, we are using the second half element to store the extra element. But in this logic, they are using the first half heap to store that extra element. That's why here yeah, there is a change in logic in here as well as the other part as well. But yeah, this works. It's almost the similar logic there. And please raise your hand or post something if you are watching this, and if you have any questions about the approach. I'll make sure to explain it again. Okay. So let's move on to the next problem now. Flatten nested list iterator. So we had seen this problem somewhere, or a similar problem. It's not this problem. Probably in some another list, but let's look into this one. Or it could be a different problem which is very similar. So LeetCode number 341, flatten nested list iterator. You are given a nested list of integers, nested list. Each element is either an integer or a list whose elements may also be integers or other lists. Implement an iterator to flatten it. Implement the nested iterator class. Nested iterator, this constructor class will take the nested list, initializes the iterator with the nested list. Okay. Int next element returns the next integer in the nested list, and then has next returns true if there are still some integers in the nested list, and false otherwise. Okay. Your code will be tested with the following pseudocode. Initialize iterator with nested list, and then while iterator dot has next, append iterator dot next to the end of the result. Return result. If result matches the expected flattened list, then your code will be judged as correct. Okay. For example, here 1 1, so this is a nested list, so that would be flattened and output to the normal list, or a one level list basically. By calling next repeatedly until has next returns false, the order of the elements returned by the next should be 1 1 2 1 1. Okay, got it. Let's see how we can perform this one. Okay, so we are given a nested list, and then we need to implement next and has next, and it has to be flattened as well. Okay, interface nested integer. So this nested integer type. Okay, we are implementing nested iterator now, but the nested integer interface has these methods. We can check whether it is an integer true if this nested integer holds a single integer rather than a nested list. Okay, and then get integer, the single integer that this nested integer holds. If it holds a single integer, returns null if this nested integer holds a nested list. Okay, get integer can be applied only if it is an integer. And then here get list, the nested list that this nested integer holds. If it holds a nested list, returns an empty list if this nested integer holds a single integer. Okay, so basically if it is a if it holds a single integer, then get list would return an empty list. And then if it is a single integer and then we are calling guest, if it's a list and if we are calling get integer, then that would return a null. Okay, let's see now how to go about it. Okay, let's return to this problem. So here we need to implement these three methods, the constructor, and then int next, and then hash next. We're given a nested list of integers. Each element is either an integer or a list whose elements may also be an integer or other list. Implement an iterator to flatten it. Okay, we need to implement these two methods. So what we can do is, there are a couple of ways that we can do it. So okay, let's keep going here. I'm thinking I will use a queue here, queue of type which contains a nested integer type. Queue is equal to new linked list. I think I can have this initialization here within the constructor. Okay, and then once I have this one, I need to add the nested list, or all the elements in the nested list, into the queue. Okay, I think instead of queue I can use better is, okay, let me explain why I'm thinking this way. This would make total sense. Like, all I need to do is I want to iterate all the elements in that nested list, and then I need to add it to the queue. So this will be of nested integer type, nested integer, and then I will be iterating through this nested list. Okay, so this is a list of nested integers, so it will be nested list. So now I want to add it to the queue that I have, queue dot offer nested integer. So I have added all the elements. So now my queue will have everything. Now I need to check if it contains, now I need to get the next element, but before that let's check if there is a next element in the queue when we flatten it. Basically, in order to do that, what I want to do is I need to check in the queue, like, okay, if queue dot is empty, or queue dot is not empty, I mean our queue is empty, then just return false. Basically, that would be one of the base case, return false. If queue is not empty, then what I'll do is nested integer current is equal to queue dot poll. So whatever we added first, that would be coming back first here. And then if the current dot is integer, whatever the interface that they have given here, I can check if it is an integer or not. So if it is integer, then what should I do? I should just return it as true. If it is not an integer, then basically I need to flatten it. If it is not an integer, then I will take it out of the queue, and then I need to make sure that I am okay. How to go about it? Okay, I already polled here. Instead of poll, I will do peak. Okay, so if it is not an integer, then I will take it out of the queue dot poll here. Now I'm polling from that queue, and then I will iterate through that basically. In order to iterate through that, if it is a okay, so here get list would return list of nested integer, and if it is not an integer, that means we can perform get list operation on top of that. That means, so that's what I'm doing here. Nested integer or nested list is equal to current dot get list. Okay, current dot get list. Okay, so now we got the nested list, and then I'll be going through each of those. Int I is equal to how to go about it. So now the problem for me is I have already added all the elements. For example, here 1 1 1. Okay, this was the case, let's say. Okay, my stack contained, or my queue contained, okay, this is my queue. Okay, when I was adding here, and my input is this way, input nested list, here's this one, input nested list is this one. Okay, so I just check this is a nested and this is a nested integer, and then this is a nested integer, and then this is a nested integer as well. So I added this one, this nested integer into my queue. Let's visualize the queue in this format here. This is the first element that came, and then I added the next element 2 into my queue, and then I have added 1 1 into my queue like this. Okay, now when I'm checking, okay, and then when I'm trying to check has next or get the next element, then in the queue whatever we add first, that will be first in will be the first out basically. So this would be removed, and then like in the has next method I need to flatten it when we are checking, because this could be just an empty list as well, without any values. Like this could be something like this also. So we need to make sure that there are elements in that in order to make sure that has next returns true. Okay, so here when I'm doing that, okay, I checked if it is an integer type. Current is an integer type, so current is not an integer type, it is a nested list type. So what I'm doing is I got the current dot get list. Current dot get list would return this list. I need to flatten it now. For nested list or nested integer, I mean nested integer, and then this will be the nested list that I queried. If like whatever I receive here, that should be added to the queue again. Okay, so that should be added to the queue. So queue dot offer this nested integer. Okay, so after adding this one, okay, I cannot just return false or true here. I need to keep doing this until the queue is not empty. Like basically, let's say if there was no elements in this list, then effectively I didn't add anything. Like as I mentioned, if it was an empty list, if it was like instead of 1 1, if it was an empty list, and if it was an empty list, and here also there was nothing, here also if there was nothing, so this would have ended up in an empty list, and then I could have returned false there. Has next, for has next I could have returned false, but in this case I can't do that. So while queue is not empty, I'll keep performing this operation. So I can add this under that loop, and then at some point one of the element will be an integer at the queue, and then that would return true. Otherwise I would return false. But my ordering went wrong here. That's what I'm concerned about. So while explaining this, okay, this 1 1 came, and then I took it. So I'm adding it back, like I'm adding it back to the queue here, the nested integer. Okay, in this case I took this, pulled this 1 1, and then the single integers will be of the integer type. I checked that this is of the integer type, but irrespective I removed it, and I'm iterating through these things, and then I added the 1 1 that will be added to the end of the queue. So 1 and 1 like this, and then I check the top of the queue again, and this is of an integer type, and then I returned true here. And then if I do next, that would return 2. But what I wanted it to return 1 here. Like whenever I do get me next value, it has to return 1. So queue wouldn't, that's the reason queue is not fitting in my criteria or my scheme of things. So let's switch to a stack, and instead of queue. So I did all this to explain why queue is not working. That was my initial first intuition that wasn't working. Let's use a stack now. Okay, I'm using a stack now, and let's add it to the stack. And also to the stack, I don't want to add it from the beginning, because if I added all the elements from the beginning, that would go and sit at the bottom. Like for example, this 1 1, these things. Okay, if I add it to the stack in the same order, so this 1 1 would be at that bottommost, and then 2 will be added after that. Okay, 1 1 would be the bottommost, and then I will add 2, and then I will add 1 1 to the at the top of it. Okay, here both are same value, so it might work, but let's take another example. Okay, let's see this 1 comma 4 comma 6. Okay, let's look into this example here. Okay, I came across this list. In the list, this 1 is one of the item, so I added that 1 into the stack, and then I came across the next nested integer, which is of this value, and then I'm adding it to the top of the stack here. Okay, and then in this case, let me like if I added 1 first, that would have went down. Now when I'm trying to see next or has next, then it is returning this 4 and 3 to the top. That's why I should not iterate in the positive order. Instead, what I'll do is, for int I is equal to nested list dot size minus 1. So I'm iterating from the reverse order, and I is greater than or equal to 0, then I minus minus. Okay, and the stack dot offer nested integer or nested list dot get I. Okay, so I'm adding it from behind. So basically the last element is 4.6. I added it to my stack, and then the next element from the last is 1. So I added it to the top of the stack. Okay, so now in the has next method, if the stack is empty, then I can immediately return false. There's no element if the stack is empty. Okay, if the stack is not empty, then I'll perform this until the stack is empty, and the nested integer is equal to, I will check the stack.peak. When I do stack.peak, if the stack like that would be the current element, and if the current element is an integer, I am returning true. Like in this case, the peak element is an integer, So I'll be returning true. So that is done. So let's assume that okay, somebody did check has next, and then they removed the first element also from there. And then if in case if this was an array instead of a single integer, let's assume that this was something like this. This was a nested integer as well. Okay, if this was a nested integer like this, then what we should have done? So we couldn't return true here, and then I poll it from the stack, or pop it from the stack, basically pop it and open from the stack. And then here I have the reference for that peak element anyway in my current element. And then what I'm doing is, if it's not an integer, then it must be a list, current.get list. And then I need to iterate through that and add it back to the stack. Again, I cannot add the first element. First element, like, okay, if it has one element, so it works. So let's assume it had two elements. Okay, like this, 1 and 2. If it was the case, my whatever I get as the first element should be the first element itself. Okay, like if I'm like, okay, if I get this list and if I'm iterating it from one by one, then I will be adding one to the stack first. Like I pulled it or popped out of the stack, and then I added one, and then I added two, which will sit on the top. And then when I see, okay, if it has next, okay, I'll get the two in the beginning, which is not the right order here. So in order to avoid that, what I need to do is I need to again iterate it from the last index. So what I'll do is I'll do the same thing, whatever I did here. I'll iterate from the last index. So okay, int I is equal to, because I have named it similarly nested list here, I is equal to nested list dot size minus 1, I greater than or equal to 0, I minus minus q dot offer nested list dot get of I, and it's not we are not offering it to the queue, we are pushing it to the stack. So I pushed it to the stack, so that came on the top. So okay, this should solve the problem for us, like whatever we were thinking. And then whenever we need the next element, first thing is we can check if it has the next element. Like if it has the next element, then what? Okay, if it has the next element, then we will return. Otherwise, we won't return. So okay, otherwise it should return null. Okay, and also another thing is we are flattening flattening our data type, whatever the nested integer type, within this has next method. So we cannot just return the next element like this without flattening. So we have to check it here. So what I'll do is, if I mean, that is one reason, and also a good practice is if has next, then return false, or if not of has next, then return false. Otherwise, just return stack dot pop, like, because we have to take it out of the stack, and then dot get integer. Okay, so the get integer would return the integer value of that nested list. So yeah, this should work. Let's see, let's run this one and see. Okay, this is the example that I had written. I haven't commented this part. Okay, stack.offer, instead of stack.offer, it should be stack.push. Okay, return false here. Okay, we cannot return false because it's not a null type. Okay, here it was given, okay, int next returns the next integer in the nested list. Like there was no question of what if did not have anything, then it returns null. So I'm just returning null. Okay, so this one works, and let's submit this if there are any other cases that we are missing out. No, so this one works. This seems like a cleaner approach, easy to understand and intuitive as well. So let's leave it at this one. Let me know if anybody has any questions. Yeah, this is a good exercise. to understand recursion, to understand how the flattening is working in multiple levels or hierarchical levels here. Yeah, let's move on to the next problem now. So here the next problem is spiral matrix. Okay, so given M cross N matrix, return all elements of the matrix in the spiral order. Okay, 1 2 3 6, okay, like this. And here it doesn't have to be like, it's not N cross N matrix, but it is M cross N, as they have clearly mentioned in the question here. And then it goes this way. Okay, so yeah, there's a pattern that we can follow here. Let's see, the spiral order. I have just initialized output in order to hold the output as we keep iterating through. And then matrix dot length, if matrix dot length is 0, then just return the empty array that we just initialized. Otherwise, left is 0. Initialize these four variables. Left, starting with left as 0, so we are starting here left as 0, and then right is matrix dot length, matrix of 0 dot length. So matrix of 0 is this row, matrix of 0 dot length is the right, or matrix of 0 dot length minus 1. So this, it points to this this row number. And then top is 0, so top is we are at the top now. And then bottom is matrix dot length minus 1, so this is the bottom. Now let's see, while left is less than or equal to top, left should be less than or equal to right. Okay, while left is less than or equal to right and top is less than or equal to bottom, we keep going. And then here, first thing is left to right. Let's keep going left to right. For int I is equal to left, I less than or equal to right, I plus plus. Okay, I is equal to left and I less than or equal to right, I plus plus. Spiral order dot add. Okay, we are adding it to the output here. Matrix of top, comma, matrix of top and I. Matrix of top is like, okay, we are in the top level now. Top and I, basically left to right. Left to right means top and whatever the iteration that we are doing. Okay, and then once we do this one, once we are done with this, we are doing top plus plus. Top plus plus means top was pointing to 0 now. So top plus plus means top would go to this one. Next time when we refer top, that would be pointing to this second row instead of the first row, or instead of the 0th row, it will be pointing to the first row. Okay, and then now the next part is, once we are done with left to right, we need to go from top to bottom. Okay, so in this case, for I is equal to top, I already, like, okay, this was the top and we already took 3 in the output here. So the top was like, we had to increment the top because it has to point from here. Okay, from top to bottom. For I is equal to top and I less than or equal to bottom. Bottom was initiated to matrix dot length minus 1. Okay, I less than or equal to bottom and then I plus plus. And then spiral order dot add, if somebody can say, in this case, the column value is constant, but the row value is varying. So the row value is varying. So the row value is like initiated to top, and then row value becomes I. And then the column value is the rightmost column. Basically, that would remain constant as right. Okay. And then next thing is bottom left to right, or bottom right to left. Okay, so in bottom right to left, if somebody can see here, this one is already printed, so we had to do right minus minus. So we are done with the rightmost column, so we did right minus minus, and we have to start with 8 here. So in this case, in order to perform right to left, we are again checking one more constraint here, if top is less than or equal to bottom. So once we did this one, basically we are checking that because we incremented the top in between. Like, we had checked if top is less than or equal to bottom in the while loop here, But again, we ended up incrementing the top after this first left to right iteration. So we are again making sure if top is less than or equal to bottom. Still top is less than or equal to bottom because top is pointing to this one and bottom is pointing to this row. Okay. And then in order to go from right to left, what we will do is for int I is equal to right, we are starting at right, and then I greater than or equal to left, and then I minus minus. Okay, spiral order dot add. In this case, the row is constant. For example, the row is the bottom row. So the row is matrix of bottom, and then our column keeps decrementing. So which is here, column started from right and it kept decrementing. So we are following that variable I. And then once we are done with this, bottom minus minus. So bottom is decreasing. So this was 0, 1, 2 at the second row. Now it became first row. Okay, and then now again bottom to top. Bottom to top means again I'm checking if left is less than or equal to right. That's for the same reason that I explained why we checked top is less than or equal to bottom, because we ended up decrementing right here. So again we are checking if left is less than or equal to right. Yes, left is still less than or equal to right, because we haven't incremented left. Left is still at 0 and right we decremented it once. So right became 1. Okay, so bottom to top, now we have to go. So what should we do? For int I is equal to bottom, now it is pointing to the bottom, and I greater than or equal to top, I minus minus, spiral order dot add matrix of I. Okay, matrix of I and left. So left is the constant. This column is constant in this case, but we are going from bottom to top, so the row value is decreasing. So the row value is whatever we have, that is the I here, that is varying here. And then once we are done with this, we have to increment the left. So the left became the next element. Once we are done with this, I think we printed 7 and 4. Now 5 is left. Okay, so here if you observe the condition here, if the left is less than or equal to right and top is less than or equal to bottom, so now actually our left value is equal to right. So I incremented the left, and left started pointing to 1, and then I decremented the right. So right started pointing to 1. So left equal to right, and then top was 0. So I incremented the top became 1, and bottom was 2, and I decremented the bottom. So bottom became 1. So now top is equal to bottom. So this condition still holds good. So we are coming here and we are doing left to right here. So I is equal to left, which is I is equal to 1, and then I less than or equal to right. Yes, it is less than or equal to right, and spiral order dot add matrix of top is 1, and then I is 1. Okay, I just added that, and then yeah, I became, like, we are incrementing I here. I is 2 and I is not less than or equal to right as of now. So this condition fails, we come out, and we are incrementing the top here, top plus plus. So now if we check this condition, I is equal to top, and I already incremented the top. So top became 2 now, and top is not less than or equal to bottom. So we will come out of this, or we will be out of this one without executing any statements. And then right minus minus. So we are at the end of this one. We would have printed all the elements in this list. So yeah, basically we need to initialize in the gist, we need to initialize left to 0 and then right to whatever the rightmost column, matrix of 0 dot length minus 1, and top to 0, and then bottom to the bottommost row, matrix dot length minus 1. Okay, and then while left is less than or equal to right and top is less than or equal to bottom, we are doing left to right. We are going left to right, and we are going top to bottom, and we are going right to left, and then we are going bottom to top. So when we did go left to right, that means after that we need to increment the top, because okay, we took one element from the top, so we incremented the top. And then once we did from top to bottom, okay, we are done with the rightmost column, so we will decrement the right. Okay, and then once we are done from right to left, okay, we just got the leftmost or this one. Okay, we did from right to left. we moved from right to left. Okay, we executed one of the bottommost element as well. So we decremented the bottom minus minus. Okay, and then when we did from when we went from bottom to top, then that means we are done with the left column also. We incremented the left, and also here we are checking top is less than or equal to bottom and left is less than or equal to right, even after checking here, because we ended up incrementing the top and right and decrementing the right here. So that should give us the proper order. Please let me know if it is not intuitive or clear, if you have any questions about it. Let me run this problem or program once. Okay, it works, and then the submission works as well. So there's nothing to do. Let's move on to the next problem. Okay, design a circular queue. Okay, LeetCode 622. So LeetCode 622, design a circular queue. I don't at least recall solving this problem anytime before. So design your implementation of the circular queue. The circular queue is a linear data structure in which the operations are performed based on FIFO, I mean first in first out since it's queue, FIFO principle, and last position is connected back to the first position to make a circle. Okay, got it. It is also called ring buffer. Okay, it is also called ring buffer. One of the benefits of circular queue is that we can make use of the spaces in front of the queue. In a normal queue, once the queue becomes full, we cannot insert the next element even if there is a space in front of the queue. But using the circular queue, we can use the space to store new values. Okay, implement my circular queue class. My circular queue of k, okay, initializes the object with the size of the queue to be k, and in front gets the front item of the queue. Okay, if the queue is empty, return -1. Int rare gets the last element or last item in the queue. If the queue is empty, return -1. And enqueue inserts an element into the circular queue, returns true if the operation is successful. Okay, enqueue, and dequeue deletes an item from the circular queue. Okay, isEmpty checks whether the circular queue is empty or not. IsFull checks whether the circular queue is full or not. You must solve the problem without using the built-in queue data structure in your programming language. Okay, let's think about it. There are so many methods to implement, but it's basically a queue which is connected from rear to front, and we can keep iterating through it indefinitely. Okay, so they mentioned the point about reusing the spaces. Okay, we can make use of the spaces in front of the queue. In a normal queue, once the queue becomes full, we cannot insert the next element even if there is a space in front of the queue. Okay, that is the thing. What we can do is we can use the, like, usually in these types of problem, usually we come up with using an array or a fixed size array or some data structure like that, because here in the initialization also they have provided a k as a parameter, so that's the capacity of the queue. And then once that is done, that should point to the first element basically. So we should maintain 2 pointers, front and rear, as they mention here, and we can keep track of the current size to know if it is full or empty, so for the easier access. And then okay, let's see how we can solve the other things here. So let's start with the implementation here. Let's start with the using an array into this one. So int integer. So I'm calling that queue as an array. Okay, and then what else we need? We need a size. We need something to hold the size, and then also we need something to hold the capacity also. I mean the maximum capacitive size is the current size. Okay, so in this case, okay, this should be an integer. Okay, in this case, when they, since they are passing k as the capacity, let's just add that first. That's an easy one. And then to our queue, we are initializing with, okay, integer type, and the size is k that they have provided. We need a maximum of k elements. And then size we are initializing to 0 at the beginning. Let's see, now we need to enqueue. When we need to enqueue something, we should see, first thing is, okay, when before we enqueue, we need pointers to at least store the first element or the first index and the last index. So let's how to do that. Let's start with the front as 0, and then what last, or we can call it as front and rear, as they have been calling it. So let's add pointers to point to those things. Okay, and initially front is pointing to the 0th memory location, and rear is also pointing to 0th memory location because there are no other elements. So now we can determine if it is full or not. How do we know if this is full or not? Or how do we know if it is empty or not? First thing is, let's check if it's empty or not. If private like what it should return, boolean is empty. Is there a method for that one? Okay, there is a method that they have defined already. So how do we determine if it's empty or not? So what we can do is return size is equal to 0. If the size is 0, then that means it is empty. And how do we determine if it is full or not? Return size is equal to capacity, or the initial capacity that they provided, the k that they provided, we assigned it to capacity. So if the size is equal to capacity, then that means the queue is full. And then the remaining thing is enqueue and dequeue. So for enqueue method, let's see if it is empty. Okay, first thing is, let's do this check of if this one is full, if this queue is full, then we cannot add anything, so we can just return false. Otherwise, what we will do is data of or whatever we added, queue of like we are pointing the rear element to the last element. So okay, so okay, let me queue of rear is equal to whatever the value that is being passed here. And then what we should do, now, okay, it keeps pointing, and okay, in the queue element, first in first out. Okay, so two things that we can think. Okay, it's even though it is fixed size array, we need some kind of offset here, because we cannot keep moving the elements across this array. Like as in when somebody removes an element, like better to give a visualization here. Okay, let's see, we are initializing a queue of size 1 2 3, okay, 4 5. Okay, so Now this is circular queue of size 5. Okay, circular queue, just to be clear, k is equal to 5, or capacity is equal to 5. Okay, now let me add, like now the front is pointing to 0, so this is okay, just to be clear, this is f, and then this is my rear as well. Okay, before we start anything. Okay, everything is empty. This is the first memory location. 11 is the first one, 12 is the second, 13 is the third, 14 is the fourth, 15 is the fifth location. Okay, and our front and rear are pointing to the same 0th location. Okay, and now if I want to add or enqueue anything into the element, so I made that here. I added to the queue of rear. Once I did that, I need to increment the rear also. Rear is equal to rear plus 1. Okay, and then I need to increment the size also once I add any element into this one. Okay, so after that I can just return it as true. Okay, in this case, if the queue was full, then I return false. Okay, and then okay, I added the queue, I added the value to the end of the queue, and then I incremented the rear element by 1, and then incremented the size, return true. Okay, in the same way, if I have to implement the dequeue, what should I do? If I have to implement the dequeue, first thing I'll check is if the array is empty or not, if or the queue is empty or not. I'm checking here. If it is empty, then just return false. I'm not dequeuing anything. If it is not empty, then I need to pick the element from the front of the queue and then return it. That's the challenge here. So what would I do here? Okay, okay, here if we see it carefully here, it dequeue just doesn't return any value, but it just deletes an element from the circular queue. Return true if the operation is successful. Okay, it just deletes an element from the queue. So in order to delete it, in order to delete an element from the circular queue and return true, okay, if the queue is empty, I'm returning false. Otherwise, I will increment my front by 1 index and then won't do anything. Basically, using the fixed memory locations, I need to give an impression that it is not fixed. Okay, let's see how I can do it. First thing is my front is, okay, front is equal to front plus 1. Okay, I made front is equal to front plus 1, and then I decrement the size by 1, and then I return true here. Okay, so this should perform dequeue. And then for the front, basically front and rear, it's easy. If the data is not empty, then we can just return front and rear also. If is empty, then front should return -1, and it should return -1. So it should return -1 here. Otherwise, it should return queue of front should be returned. Okay, return queue of front. Okay, so in the same way, rear also is implemented. Okay, if it is empty, then return -1. Otherwise, return queue of rear pointer, whatever it is pointing to. Now the problem is, okay, I see that there is some problem with this implementation, because let's say, okay, we initialized an circular queue with k is equal to 5. So let's see what all the values of this one. So here These are all my variables in this program. So the capacity value will be equal to 5, and then I created a queue with 5 different memory locations. So that is, let's say that is this one, 5 different memory locations. I don't need this one, and size is 0. Pointing to front is pointing to here, this variable at 11, and rear is pointing to this one. And now let's see this example, my circular queue that is initialized with value 3. Okay, let's see 3 only instead. Okay, 11, 12, 13. Okay, and here size is 0, front is 0. Okay, and then capacity is 3. And then here NQ1 would do what NQ1 would do. If is full, it is not full. Basically, size is not equal to capacity, so it doesn't return false. But Q of rear is equal to value. Q of rear is basically this one, so that is equal to value. Value is 1 here, so I will store 1 here in the rear, and then rear would be is equal to rear plus 1, and then size plus plus, and then return true. Rear would be is equal to rear plus 1, so rear would start pointing here to the next memory location, and then I will rear would be equal to rear plus 1, size plus plus, that would make the size 1, and I can just remove these two for now. Okay, and this one also I can remove for now. Okay, rear is equal to rear plus 1, size plus plus, return true. Okay, we return true now, so that is successful. Now the next element, NQ, one more element, which is NQ2 here. Okay, for that let's see how we can do it. So in order to NQ2, the same operation, like I am inserting it to the location where the rear is pointing to, and then increment the rear and then increment the size. So I'm NQing 2 here, and then I need to increment the rear value to the next one. Okay, and then incremented the size also to 2. Okay, and then next operation NQ3 again, the same thing. I got 3 here, I added 3 our value to that rear, and then incremented the rear to the next memory location. But okay, my rear is pointing to the next memory location. Let's see what we need to do. Okay, I didn't do anything with my front when I added, but I'm just adding it to the rear. Yeah, that is valid. When I need to DQ, then I'm removing it from the front. So when I'm adding it to the rear end. But I need a circular way of handling it. So instead of making the rear as rear plus 1, what I can do is rear plus 1 modular capacity. If I do that one, rear plus 1, and if I take the modular of capacity or size, it should be capacity, because we are looking into the overall size of the overall initial capacity that was assigned. It doesn't matter what's the current size is. Rear plus 1 mod capacity, and then okay, size plus plus. And in the same way, when we are dequeuing it, we incremented the front. Instead of just incrementing the front, what if we do front plus 1 and then modulus of capacity? Then we will be remaining within that particular memory locations only, rather than trying to get away from that one. Like we need to play within the indexes 1, 2, 3 only, because that's the capacity our data structure has here. So our front and rear should be pointing to that as of now. So let's see, now rear plus 1, rear was 0, 0 plus 1, 1 mod capacity, so it is pointing to first memory location now. Okay, and then it started pointing to second memory location, third memory location. Okay, I think this one looks good to me. Now let's look into an example step by step. Let's troubleshoot it. Like okay, my brain capacity is a little bit done now. This was a hard problem for me to imagine. So okay, what is it? Is it okay? This is marked as LeetCode medium, but this was hard for me. I had never seen this problem before. So let's see. Okay, I think let's comment out these lines as well. Okay. Okay, this memory location never existed. So it should go to, once we add the third pointer, it should be circular, and R should go point to the initial location here. Okay. And then if someone tries to remove something, I should remove it from the front. Okay, let's add a breakpoint in the enqueue method, and let's add a breakpoint in the dequeue method both, and then let's go ahead. Okay, it doesn't have any local local variables here, but let's keep going. If it is full, I don't think it is full, but if we go here, is full, and put a breakpoint. Okay, it came to is full, and then okay, it doesn't show the value of size or capacity. I wish I had a value for, I see the value for those things whenever I'm iterating through, but still it's fine. Okay, or at least the queue as well. Okay, let's keep going here. Now queue. Okay, this is of no use now if we don't see the value for these things. So what should I do is, let's add some print statements or indexes somehow, or what should we do? Start debugging sessions and watch expressions. Okay, standard output. Okay, private int queue. Okay, let's add some standard print statements. System dot out dot print println size plus size plus what else we care about, size, and then queue, and then rear and front. Okay, instead of size, let's do front, and then front, and then rear, plus rear, and then plus queue. Okay, that might just give the memory address of that one, but still I will print it here, and then I'll print it after. Okay, I won't print it here, I don't need it in the constructor, but I'll print it here before adding to the queue, and then I'll print it here after adding to the queue. And then the same way in the dequeue, I'll print it here, and then I'll print it here also. Okay, so now let's go ahead. Okay, now our debugger stopped here. Let's keep going. And let's remove this breakpoint here. Okay, we had a system.out.println here, and then front is 0, rear is 0, and then q is something. Let's make it even neater. Print q. Print instead of q, let's do print q. And we need to implement the print method. Private void print int array int num. Okay, and just to be neat, let's do this one also. Okay. Let's start our debugger once again. Okay, I think I see that Sadam is telling the same thing to add some print statement to debug. That's good. Okay, system.out.print, and there's no. Okay, let's go ahead. Man, what's now? Oh. So this one is tricky. String builder str is equal to new string builder. Okay, let's not leave it. Str.append. Let's append this one. Okay, and then let's append it here. Okay, and then let's append the last bit. Okay, we appended everything. Now this should return string. Return dot toString. Okay. Yeah, now we are again back to the enqueue debugger, and then let's see. So now I printed our initial state. Front is 0, rear is 0, and then my queue contains 0, 0, 0. So this is a static array with 3 elements or 3 memory locations, which all of which has 0, 0, 0. And then q of rear. Q of rear is equal to value now. Q of rear became value. And then rear is equal to rear plus 1 mod capacity. So rear would become, rear was 0, so rear should become 1 now. And then size also should become 1, but I'm not printing size. But let's see the print now. Okay, rear became 1, and then in the I added the value in the 0th memory location as well, and then returning true. So once that is done, I'm enqueuing more objects or more elements here. So there are more enqueue operations here, like enqueue1 and enqueue. So there is enqueue1. So this is the 3 is the capacity passed, and then NQ1, NQ2, NQ3, and NQ4. So there are 4 NQ operations. I should say 8 print statements. So let's keep going. So when we started the operations, it used to be this way, and then 2 was inserted here. And then let's keep going even further. When we started it, it was initially this state. Now 3 would be inserted there. Okay, 3 is inserted. And then now when we try to insert 4, my rear is pointing back to 0 now. Rear is pointing to 0. And another thing is when we try to insert 4, our size is already 3 now. So it should give full, and we should not even come to this one. So yeah, now it should just return false here. Yeah, it returns false. And now the next operation is rare. Okay, we are trying to get rare, and that would, rare is not giving away anything. What is the rare method? I just forgot. Okay, rare should return int, and this is not empty, so rare should return something. Okay, there's no parameter passed, and my rare should return whatever is in the 0th or whatever is in the 3rd element. So rare should return 3, but let's see what it does. 1 2 3, and okay, size minus minus. I'm dequeuing here. Okay, was there a dequeue method? Okay, I'm just putting the breakpoints in the dequeue method. So my dequeues are working as and when I dequeue. We can keep seeing here. And then once I dequeued and then enqueued 4 again, and then it worked 4 to 3. Since I dequeued 1 here, okay, dequeued 1 from this one. Dequeued means basically I didn't remove it from the array. I had it, but my front became 1 and rare became 0. So 1 to 0, 1 to 0, and it is not inclusive of rare, but it is exclusive of rare. So that's why 1 to 0, it just became only these 2 memory locations were considered. This was not considered. Now when I wanted to insert again, I inserted it in the next pointer to rare. Like rare was pointing here, I just inserted a value here. Okay, so that made it work. And then let's keep going now. Okay, so here in this case, okay, rare should return 1, and all the errors I'm getting here is in the rare operation. So rare operation should return 1, should return 3, I am returning 1, and here also rare should return 4 and I am returning 2. So the error is basically, as I said here, as I mentioned here, my rare is not inclusive, it is exclusive of rare. So what should I do is rare minus 1 modulo of this one, but what I was doing is I was just returning rare only. So let me see, where is it? Okay, rare method. Okay, here. So I was just returning rare method here. So what I'll do here is, okay, I will try to get the rare index. Okay, that would be rare minus 1 modulo capacity. Okay, and then I will get the value in the rare index. So now let's see, let's run the same example. Okay, okay, minus 1. If it goes to minus 1 modulo capacity, again it doesn't work. So what I can do is in order to keep it always positive, in case if it was pointing to 0, that means it goes to -1, like rare -1 goes to -1. So rather than doing that, anyway, we are looking at the modulo. What we can do is rare -1, just add capacity to that. So it comes to the positive value. Okay, that works. And then let's submit it and see if it works. It might time out since there are so many print statements that we have added. Let's comment out all our print statements. Okay, let's submit this one now. Okay, it works now. Awesome. Yeah, so please let me know if you have any questions for everything that we did. So basically, we needed to create a circular queue. We created a fixed size queue only, or fixed sized array only, and then we are maintaining front end rare pointers, and then we are shrinking the front pointer when we need to dequeue, and we are expanding the rare pointer when we need to enqueue, and then we are moving it in a circular manner by using the modulo operation, and then we are keeping track of the size and capacity in order to make sure whether we in order to return it is full or is empty. But as I think about it now, we might not have required the size method, or size attribute, but it makes the things easier. But let me see if I can execute it without size. Like, okay, let me leave it in the constructor, but I didn't want to use size here, like where I have used in is empty method and in the capacity method. If that is the case, like when is it full? When our array is full? Our array is full. No, I think we need size. Like I cannot determine it based on the rare and the um, based on the rare and the um, front pointers alone, because in the beginning when it was empty also, it both were pointing to the same memory location, and then when it was full also, both were pointing to the same memory location. So by having the size method, it determines. So I think it's good. Like the size attribute makes it a lot easier. Let's keep it that way. Let's go back to our list now. Okay, let me refresh. So we solved 12 out of 12 now. So let's increase our time horizon to a little longer now. Rather than this one, we made it for 3 months now, past 3 months, and then sorted based on the frequency only. But where are all the problems that we solved already? Okay, so that doesn't appear, I think, here. So let's go back to our case and let's just check here. Like, okay, let's take a break and then I'll make sure that this list is updated with all the 12 problems that we solved. Until then, take a break. Okay, here I am. I'm back. So, okay, now our longer or larger time frame list is also updated based on the 12 problems that we solved. Let's do it in like, let's try to finish 20 in this list and then move on to some other company. That's the plan. So LRU cache. A lot of problems in this are repeated with other companies as well. Excuse me. So let's look into LRU cache. This is one of the most common problem that we come across in every company's list. I will probably create a separate video explaining the solution for this problem, Basically, this gives an idea about how the caching works in our backend web applications or anywhere. Basically, how the caching works as well. There are a couple of strategies: recently used caching strategy or least frequently used caching strategy. Could be anything. So here they are asking LRU means least recently used cache. If any of you have used Google Guava library, then it is implemented, or it is implemented by using some code or implementation like this. So let's see. Problem number 146, LRU cache. Design a data structure that follows the constraints of a least recently used LRU cache. Implement the LRU cache class. So we need a constructor which initializes with a certain capacity, and then get method returns the value of key if the key exists, otherwise returns 1, and put method updates the value of the key if the key exists, otherwise add the key value pair into the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. The function get and put must each run in O of 1 average time complexity. So this is the most challenging part here. O of 1 average time complexity. So most of the logic or the complexity here is choosing the right data structure in order to maintain this LRU cache. Once we choose the right data structure, the implementation is about keeping our head calm and implementing these steps that they have laid out here in the problem description step by step. So there are a couple of different approaches. So one of the approach here that I have commented out, in this one we have implemented our own custom list node type, and we are using that to store as a we are using that with another hash map to implement this LRU cache. And then there is another approach where we are using linked hash map, that is the uh, Java language supported data structure type, and through that also we can do this. So let's look into the linked hash map for a brief, and after that let's go to a more general non-Java specific solution here. Okay, in Java, like this, it provides a linked hash map, which is a combination of a linked list and a hash map. So I have initialized, or I have taken that as an attribute, linked hash map, and capacity. So basically capacity is provided as a constructor in the as a parameter in the constructor. So I initialize the capacity here and then initialize the linked hash map. And then in the get method, all I'm doing is if the cache contains, or if the linked hash map contains that key, then if the linked hash map does not contains that key, then return -1. And then if it contains that key, all I need to do is basically I need to get the value which is in the cache, and then I need to move that value to the first position in the linked list, and then I need to return the value. So that is accomplished here. So I just took the value. I have already checked in the cache. If it does not exist, then return -1. If it exists, then it will come here. I'm getting the value from that cache. Once I have that, get that value, I'm doing this dot cache dot put first. This would move the position of that element into the beginning of the linked list, and then I'm just returning that value. And then in the put method, all I'm doing is if the and there is nothing, there's no change or nothing related to related to the size here, so I'm not checking any capacity or size here. But why you might have a question, why did I do this statement put first? Why didn't I just return this dot cache dot get key? Because this is a least recently used cache, and the least recently used ones should come to the front. Sorry, the most recently used ones should come to the front, and then the least recently one should keep going behind in the linked list, so that it will be easier for us to clear, or easier for us to make way for a newly added elements into the cache. So that's what we will see in the put implementation. So here, since we access that key, that would come in the we will move that to the beginning of the list. So in the put method here, they have provided a key and a value. So I'm checking here if the cache already contains the key. That means if the cache already contains the key, then it is just like overriding. We are not adding a new entry, but we are overriding an existing entry. So that wouldn't change the size anyway. So that's why I'm checking. If the cache contains the key, then cache dot remove the key. So if the cache contains the key, I just need to remove it from the cache, and then I'm putting the new key and value in the first or in the beginning of that linked hash map. This dot cache dot put first key value. And let's see the other scenario. If the cache does not contain that key, if the cache does not contain that key, and if the cache size is up to the capacity already, like if the cache size like was initiated at initialized at, in this example, for example, LRU cache was initialized with capacity 2, and we are at the and if we are at the capacity already, then what that means is we need to make way for the new entry that we are going to add. How do we make way for that one? We will have to delete the um, least recently used entry there. So recently used entry will be in the last. So I'm polling the last entry, and then so now the size of the cache will be less than the capacity, and then I'll do the same thing. This dot cache dot put first key comma value. I'll add that entry into the cache. So this would work pretty well. So let's run submit this. Okay, this is working. So let's comment this approach for now in order to see a more generic language independent approach. So here all we are doing is we are defining a structure like a doubly ended linked list, or a doubly linked list basically. So in the doubly linked list, we can point to the next pointer or the next node, as well as we can point to the previous node as well. So here that's what we are defining, and then the key and the value. This holds the key and the value, and then here in the so in the LRU cache, basically we have capacity, and we need to maintain the head pointer. We need to maintain the tail pointer, which signifies the end of the linked list, and then we have a map which contains which can provide easier access to see if the key exists in the cache or not. Okay, so I have named it as cache. So I'm initializing the capacity with the capacity parameter passed, and for head I'm creating a dummy node here. It could be of any value. For tail I'm creating a dummy node of any value, and then I'm just connecting the head dot next to tail, and then I'm connecting the tail dot previous to head. So since there are no elements or there are no key value pairs when we initially create this LRU cache, I'm just connecting the head to tail. Whenever we need to add something, we will be adding in between the head and tail all the elements. And then this dot cache, I'm initializing the hash map here. And then let's look into the get method. In the get method, all I'm doing is, if the cache does not contain the key, I can check it in the hash map that I created. If the cache does not contain the key, I'm returning -1. And what is this cache type? Cache type is integer to list node. That means we are storing key to the reference of that node, like reference of the node in the linked list basically. For any key value, I'm storing the reference of the node in the linked list. Okay, doubly linked list to be specific. Okay, so now here I'm checking if the cache does not contain any value for that key, then I'm just returning -1. So that is not present in the cache. Otherwise, what I need to do is, if it contains in the key, then I can point it, I can get the reference for that node in the cache. So this dot cache dot get key would return the reference for that particular node. And then what I need to do, first step is I need to remove that node from that particular position, wherever it is. It might be in the middle, or it might be in the end of the linked list, or anywhere. Since I'm accessing it now, so this would become the most recently accessed node. So that's why I'm removing the node from the cache and or the list, and then I'm adding it to the front of the list. So how I'm performing these operations, remove node and add to front. So I'll explain that one. And then so let's focus on the get method. So I'm removing it from wherever it existed, and then adding it to the front of the list, and then I'm returning the value, whatever the value for that particular key. So node to be returned, that value would return the value for that key. Okay, now let's dive deep into this remove node and add to front methods. Remove node method. So now I have the reference for that node which was stored in the cache, and how can I remove that node from in between a doubly linked list? Okay, from the doubly linked list, if I want to remove a node, basically I have a pointer to the next node as well as I have a pointer to the previous node. All I need to do is I need to connect my previous node to my next node, and I have to connect my next node to my previous node. So I will be disconnected from the linked list. So for example, I here remove node and then I have passed the pointer to this node. So this node has to be removed. So node dot previous dot next. So node's previous next element, next pointer would be pointing to node's next pointer. And then node dot next dot previous, node's next element's previous pointer is connected to directly to node's previous node. Okay, so node will go out of the picture and it would be garbage collected later since it is not referenced anywhere. Okay, so yeah, so that is about remove node. Let's look into the other method, add to front. In add to front, what we need to do is node is given and I have to add it as a next element of the head. That's the intention. So we have created a dummy head as we saw in the constructor. So I created a so I'm taking the reference of the next node of that head. So head dot next is the next node, and then all I'm doing here is head dot next is next would be the node that I need to add to the front. So that would be the head dot next, and then node dot previous, whatever the node I need to add it as a add it in front of the head. So that so I'm adding the previous pointer to that as a head. So there is a connection established between the head and the node that needed to be added to front. But one side connection is done, but I need to add the connection to the node to the next node that was already the first element in the list basically. So I'm doing is I already had taken or stored the reference for that particular node here. So I'm doing node dot next is equal to current node dot next is equal to that next node, and then next node dot previous is equal to the node that I'm trying to add. It's like simply linking and delinking. So that's all I'm doing, and all these are like O of one operations. So basically here I looked up in the get method, I looked up from the cache, which is O of one operation, and remove node, that was O of one operation because I have the reference to the node, and then add to front, that was O of one operation but just by linking and delinking, and I have a reference to the node, and I'm returning the value of that node. Basically that's it. So all of this is O of one operation. And then put operation. Let's look into the put operation. If the cache contains the key, then what I'm doing? If the cache contains the key, then I know that the node to be removed we can get that node reference from the cache. Okay, I got that from the cache, and then I have to remove it from the node basically, because I'll be overwriting the value for that, and also I need to add it to the front of the list instead of having it somewhere in the middle of the list. That's why I just removed. If the cache already contains it, I'll remove it because I'll anyway be adding it to the front. Okay, and then list node to be added. I'm creating the node to be added. I'm given the key and value both in the parameter here. Even if the cache contains or not, it doesn't matter. I'm creating a new node here that has to be added. New list node of key and value, and then add that node to the front of the queue. So add to front, node to be added. So whatever I created here, and then I'm adding it to the cache as well. This dot cache dot put key comma node to be added. Actually cache had, if the cache contained the previous key, then this will just override the value of that key with the new node that we have created here. And then here, if after adding this node, if the cache size exceeds, let's say if the cache did not contain it, and if this is a new node that we have added, if the cache size exceeds after we added that new node, then what we should do, we should remove the last entry of that linked list. So if the cache dot size is greater than this dot capacity, then list dot node to be removed will be like remove last. So I have to remove the last node from the linked list first thing. So remove last, how I am doing it? So I have to remove the previous node of the head of the tail pointer that we created in the beginning. So node to be deleted is equal to tail dot previous, and then once I get the reference for that node, I can call the previous remove node method that I had before. Like I got the reference of that node. I'm calling the remove node method to be deleted, and then return to be deleted node. So why I'm holding a reference for that, because once I remove the node to be deleted, like node to be removed, I'm removing it from the cache as well. So in order to removing it from the cache.remove node remove.key. Like I have the key as the key and value would be the node value. So node remove.key would remove that from our hash map as well, which is named as the cache here. So that should be it. Let's run this one once and then see. Okay, so this one works, and when I submit it, this works too. So this is the basic implementation of a LRU cache. Just remember that we need a linked list, a doubly linked list, and we need a hash map in order to implement a LRU cache. And then just read these statements or the descriptions with very carefully, and then this would give us the steps in order to implement it. So make sure that we have to make sure that all the operations that are performed are O of 1 operations. Since we use doubly linked list, we don't have to iterate through that array. If we get the reference of that one, since we use the hash map, we get the reference of those nodes directly from the hash map if given the key. So that's about the implementation of this problem. Let's move on to the next one. Okay. Okay. So LRU cache is done, and these were already done. Valid palindrome. This is a LeetCode easy problem. Let's not take more than 2 minutes for this one. Okay. Problem number 125, valid palindrome. And then it's a LeetCode easy. A phrase is a palindrome if after converting all the uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters includes letters and numbers basically. Given a string s, return true if it's a palindrome, otherwise false. Okay, so basic here, like we should the catch is we should not consider the space, comma, and other special characters. We should just consider alphanumeric characters and see if it's a palindrome or not. So I'm doing is I initialized 2 pointers, one from the beginning and one from the end of the string. So one I initialized left to 0 and right to string dot length -1. And then I'm checking while left is less than right, always when left is less than right. So these two steps that I'm performing while left is less than right and not of character is letter or digit, s dot caret left plus. So here, as long as the left is pointing to any space or any special characters, I'm just keep iterating up to getting the next alphabetical or numerical character. Okay, the same thing I'm doing here. While left is less than right, I need to keep checking if the left is less than right inside as well. And if not the character is a letter or digit, I'm just um, decreasing right pointer and then keep iterating it. Okay, it keeps coming down here, and then if once this is done, both will be pointing to a valid alphanumeric character. So I'm checking if character dot to lowercase s dot caret left is not equal to s dot caret right, then I will return false. After that, I'm doing left plus plus, right minus minus. I mean, basically, like this is a post increment and post decrement. So this will be performed after this operation itself. But if this is not equal, then I'm returning false immediately. But if this is equal, I'm not returning true immediately, but I'm checking all the characters. Once I increment the uh, increment the character here and decrement the character here, I'll check the next character. So in this example, if we see, I increment one is pointing here, one is pointing at rightmost this one. So a is equal to a, and then I come back here. Left is still less than right, and then there is a space here. So left would be incremented until the next alphabetical character, that is m. It will be pointing to m here, and left is less than right, but right is already pointing to an alphanumeric character, which is m. So I'll come back this one. It will be skipped. I'll skip this one. And then if character dot is to lowercase, I'm character dot to lowercase at left, which is m. If it is not equal to character at right, lowercase dot right, which is m, then I'm returning false. But they are equal, so I'm not returning false. I'm going back again. Again, I'm pointing to a, and here also it is pointing to a. So until I come to the middle, or until the left will be less than right, I keep comparing, and then all of them come true here as long as it's an alphanumeric character, and then I end up returning true for this example. Another way of implementing is, if someone gets confused about like, okay, why we need to have a loop inside this one, all we can do is like, okay, to simplify this one, so let me run this example at least, since I explained it. Okay, so this one, this one's running properly. So another way could be like, if character dot to, like, okay, if not of character of, okay, let's see this one. All I'm doing here is, if not of character, is letter or digit at left, or this one. Okay, no, let's do this one. Then instead of, for while loop, all I'm doing here is left plus plus, and then continue. Let's not do this one, like it's going step by step here, and then here. Okay, instead of while loop, if I need to just have a if condition, if that feels easy, and so I'll do right minus minus and continue to the next step. Okay, I'm not returning false or anything, I'm just continuing by incrementing this one. I'll comment out this code, and then let's run this one. Okay, start caret left. One, two, one, sorry, 1, 2, 3, 2, 1. Okay. Okay, you can see this one works too. And when I submit it, it's almost the same performance. Basically, rather than looping within the loop here, where I need to check the constraints again, I'm checking the if condition, and I'm just keeping it to the next loop here. Like this while loop takes care of what I was doing it in this while loop here. So this should be, if this is more readable for some people, let's like just implement it using this approach. Okay, let's move on to the next problem now. So LRU cache valids palindrome, and then here kth largest element in array. So kth largest element in array. Usually this is like this is always a problem with like whenever I get a kth largest or kth smallest element in the array and all those things, it's mostly using priority queue or a heap. So here, given an integer array nums and an integer k, return the kth largest element in the array. Note that it is the kth largest element in the sorted order. Kth largest in the sorted order, not the kth distinct element. Okay, can you solve it without sorting? So they're asking like, okay, one simple way of doing this one is if we just sort it, and then we iterate to kth position in the array, then we would get the array from the end, then we would get the kth largest element. How can we do it without sorting? And sorting would take n log k, n log n, in order to sort the lists of size n. So here k is 2, and I need to get second largest element basically. So in order to do that, can I do better than n log n? Yes, I don't need to sort everything, but I need to retain top 2 elements basically, since that k is 2, top 2 elements all the time basically in my data structure, and then I'll return the second element. So how can I retain the top 2 elements? In order to retain the top 2 elements, I'll create a min priority queue or a min heap. So as you see in this implementation here, we can create a min heap, and then I'm iterating through the numbers, or iterating to the elements in this nums array, and then I'm adding it to the min heap. And if the min heap size exceeds k, at that point I'm just removing the element from the min heap. When I remove it, it will, like, okay, when it exceeded, let's say a k value is 2, so I'm checking if the min heap size becomes 3, then I will be uh, uh, removing one element from the min heap. And when I do min heap dot remove, what does it remove? It will remove the minimum element from that heap. So it will remove the third largest from that heap. So I'll still retain the top two largest elements in that heap all the time. And at the end, it would just retain the top two largest elements. And for every add operations, it would take log k. Log k in this case, log 2. So that is much better than log n. So in this example itself, if we consider, the array size is 6, so it would have taken 6 log 6. But in our case, for 6 elements, when we are adding to priority queue, it would take 6 log 2 or n log k. That's the time complexity. So this works the same way. And there is another approach where we can use quick select in order to find the k largest element. Quick select is nothing but it is like a quick sort. I'll come to that one once we execute it. Okay, I'll just tell the gist about quick select. Let's not go in deep into that one. So in quick select, first thing is, let's keep the problem statement in our mind always. And if this problem is given, I will any day implement it using priority queue. But I still looked into the quick select approach because I wanted to be aware of that approach, and if I can use that in some other problem, it's all good. So here, okay, we find the kth largest element, and I've written a quick select method. In quick select, I've written a recursive method here. In the quick select recursive method, all I care about is I need to get the top k elements on one side, and then the bottom k, and then the bottom rest of the bottom elements on other side. I do not care if those are if all of the bottom k elements are sorted or not. The top k elements should be sorted, and until I get the kth element, I keep sorting or keep looking for it. That's the gist of the solution here. So here I added the input to an input array or input list here. This makes it easy. So here and then I'm creating this quick select method, and every time I create I assign a pivot index or get a pivot index by getting a random element uh, in the num start size. Okay, and then the pivot element would be the element in the pivot index, and then I will segregate it into three classifications: all the elements that are greater than the pivot element, and all the elements that are less than the pivot element, and all the elements that are equal to pivot element. Okay, I segregated into three different groups. And now this is the important part. Pay attention. So here, I created these three groups, and then I segregated it in those three broader classification lists here. Once that is done, I'm checking here if k is less than greater than pivot dot size. Okay, that means if k is less than greater than pivot dot size, greater than pivot, like all the greater than pivot elements are there in one of the list, and if k is less than the size of that, that means I have all the k largest elements are more than k largest elements. It could be k plus x. Okay, k plus x largest elements in this one, and all I care about is the top k largest elements. But this has more than top k largest elements. It has top k plus x elements. Okay, so I can reduce my search space into, I can call the same quick select method using this array, greater than pivot array, and I'll pass the k itself because I need the top k or kth largest element. Okay, and then in another case, in case if greater than pivot dot size is not greater than k, if that's the case, I'm checking if the greater than pivot dot size plus equal to pivot size is less than k. That means if the greater than pivot plus equal to pivot, if both these combined both these arrays size combined also doesn't becomes k. That means, okay, I have like so that means there are so many elements equal to like whatever the pivot we choose, greater than pivot and less than pivot, that that doesn't make up for the top k elements, both of these lists. Based on that, or sorry, greater than pivot and equal to pivot, that both of those two doesn't make up for the top k elements. Then the top, like then I have to consider the elements within the less than pivot as well. Okay, how do I consider that? How do I consider that? There is a smart way of doing it. Like I will get the size of the greater than pivot and I'll get the size of the equal to pivot. Let's say those two, like I know that my k largest element is in less than pivot because both of the like including this size of both of these, it's not k. So my k largest value is in less than pivot array. But if I know the size of this one, let's say my k is 10. Okay, and the combined sum of greater than pivot contains, let's say, 4 elements, and then equal to pivot contain 1 element. So I have 5 elements including these two, and then my k is 10. Okay, that means I can rule out, okay, 5 elements greater than the pivot are already here. So I need to find the fifth largest element in this less than pivot. Like rather than finding 10th largest, now my problem reduced to finding the fifth largest element in this less than pivot element. Okay, less than pivot array. That's what I'm doing here. Return quick select of less than pivot k minus greater than pivot dot size minus equal to pivot dot size. Okay, and then after reducing my search space again and again, and finally I will just return pivot here. Like if none of these conditions get satisfied, if neither of these conditions get satisfied, that means the pivot element is the answer for me. So yeah, if like yeah, if k is less than greater than or pivot, okay, if either of these two conditions doesn't satisfy, then I'm just returning pivot here. Let's run this example once. Awesome, this is like 73%. Okay, so let's move on to the next problem now. There is another approach actually. It is called bucket sort or counting sort, I guess. Like basically, this is not at all ideal when my list is sparse. Like for example, if I have a number as 1 and if I have next number as 97 and then 1023, basically this is not the approach to be used because we are all arranging all the elements into different buckets, buckets, and then we are trying to use binary search within that bucket. So yeah, let's not worry about it, but just to be creative in problem solving in some interviews when we are thinking through. Let's see, find kth largest element. I have the min element, I have the max element here, and then like after I know the min and max element, I can create a bucket with the size of max minus min plus 1. So I need to uh, create a bucket of size maximum and minimum in between that, and then I'm incrementing the number within that bucket. Like if the number exists, like okay, if like let's say my lowest number or minimum element is 0 and maximum element is 1000, just to keep it simple. So I will create an array of 1000 elements of our size 1000. Okay, and then if the number present is 0, then I will increment the 0th index by 1, and if the next number present is 97, then I'll increment the 97th index by 1, and if there is another 97 at some point, then I'll increment the 97th index by 1 more. So 97th index will have 2. Okay, and then if I have next number as 130, I'll increment 130th index by 1. So I do that, I arrange my numbers that way, and then in remaining k, I'm just looking through those buckets from 0 to from bucket length minus 1, from 1000 to down, like down to k, and then by looking into that, like I keep reducing it as and when there are elements in the bucket, and then I'm just returning the um, value or that bucket's address or bucket's index whenever I reach the remaining is equal to 0. Okay. If I don't find that element at all, then return -1. Let's see this. Okay, works great for this examples here. Okay, let's refresh my list again. So we are done with the 15 problems now. So there is two sum. I think it goes to 2 basic, and there is decode string, 3 sum, valid parenthesis, reverse. Okay, we need to, like, if we are selecting to do solve 5 more problems here. There is move trees, move zeros, and then implement try. I would love to see implement try. I haven't seen it in a long time, I guess, or a very long time, I would say. So okay, let's move to twosome and just take a look into that briefly. Okay, in twosome, basically, it's a first problem in the LeetCode, and it's a LeetCode easy. Given an array of integer nums and an integer target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. Okay, in 2, 7, 11, 15, target is 9. So 2 plus 7 would make 9. So I'm returning the index 0 and 1 correspondingly here. And 3, 2, 4 is given, and target is 6. So 4 plus 2 would make 6. So the index is returned as 1 comma 1, and here target is 6, 0 comma 1. That's the combination would return the target. So how do we do that? So one way of, like, brute force approaches, like when our mind is thinking about the solution, we think in way that, okay, with 2, what all elements with make up the target, and with the 7, what all elements would make up the target. If we go that way, it would be O of n square solution. What else we can do? So let's keep doing, like in this example, or in this code that you can see, I have used a hash map. So I have named it as complements map, and as we keep iterating through this array, let's say I iterated through, I went through 2, and then I checked in the array, checked in the complements map. Okay, what is the complement I need? I'm looking for, okay, I have 2 now. I'm looking for if there are difference between 9 minus 2, difference between 9 minus 2 present in the map. Okay, 9 minus 2 is 7. I'm looking if the 7 exists in the map. No, it does not, because I haven't added anything. So I won't do anything if it does not if the complements map does not contain that key. I won't do anything, and I'll just add the element into the complements map with its index. Okay, I added 2 into the complements map, and then I came across this next element 7. So now I need to check the complement here. So what's the complement for 7 here? 9 minus 7, 2. So now the complement is 2, and I'm checking in the complement map. Okay, if the complement map contains the value 2, yes it does, we just added it in the beginning. So I'm just returning the result here. Like I is the index of the current element, which is 7, and a complement map dot get 2 would return the index of 2, which is 0. So I'm returning 1 and 0 in this case. So yeah, and they haven't cared about any order here. So 1 and 0 is same as 0 and 1 here. Let's look into this example. If we are looking into this example, okay, target is 6. So I'm iterating through this list. Okay, I came across 3. I'm checking, okay, complement value with 3 is 6 minus 3, 3. I'm looking if there is a 3 exists in the map. No, it does not. So I just add 3 to the map, and then move on to the next element 2. Next element is 2, so 6 minus 2 4, so the complement is 4. I'm looking if the complement map contains 4. No, it does not. So I move on to the, so I just add 2 to the map again, complement map, and then I move on to the next element, which is 4. And then here for 4 the complement value is 6 minus 4 is 2, and I'm checking it in the map if the complement value, which is 2, does it exist. It does exist because I just added 2 value here, and then I'm returning the indexes of those elements here. So as simple as that. Nothing complicated here. I'm using additional space O of n space in this, and then O of n, only one iteration we are doing here, and it will be O of n solution. And let's submit this and check it for ourselves. That's done. Okay, so the next problem is decode string. Let's see decode string. Okay, so decode string is like LeetCode medium problem. Okay, so it's a LeetCode 394 problem, decode string, and we need to find the solution for that one. So in this case, given an encoded string, return its decoded string. Okay, the encoding rule is k of encoded string, okay, where encoded string inside the square brackets is being repeated exactly k times. Okay, k of encoded string, where encoded string inside the square brackets is being repeated exactly k times. Note that k is guaranteed to be a positive integer. Okay, so now this is k. 3 in bracket of a means a, and then 2 in bracket of bc means 2 times bc. Okay, and 3 of a2 means, okay, 3 of a2 means 3 of a2 will be, okay, 3 of a2 of c. So in this case I would just first convert, this will be ACC according to me, and 3 of ACC will be ACC. Okay, from the innermost innermost loop we keep decoding it. Okay, got it. So this makes sense, and here also it's the same way. 2 ABC, and then 3 CD, and then EF as it is. Okay, so here there is a nesting of the encoding, not just the encoding. You may assume that the input string is always valid. There are no extra white spaces. Square brackets are all well formed. Furthermore, you may assume that the original data does not contain any digits, and that digits are only for those repeated numbers k. For example, there will not be an input like 3a or 2 of 4. Okay, the test cases are generated so that the length of the output will never exceed 10 power 5. Okay, always the resultant output will be alphabets. Okay, that makes sense. So here, as I'm thinking the approach, since there is nesting, the first thing that comes into my mind is either recursion or using a stack. So we need a stack to keep track of, like basically the nesting there. So so how do we do it using stack? So we can iterate through all the characters, all the entire string, character by character, and then if there is a digit, if we encounter the digit, then we need to do is calculate the k. Okay, and k could be 1 is less than all the integers in S are in the range 1 to 300. Okay, it doesn't have to be a single digit, that it can be a number as well. So we need to read the number and then and then we need to add it to the stack. Okay, so if it's a digit, calculate k and then add it to, okay, or else if it's a open braces, then what should we do? Okay, sorry. So here, okay, I lost my train of thought because I was looking into something. I was checking my email and okay, let's get back here. Given an encoded string, return its decoded string. The encoding rule is k of encoded string. Okay, I got it. Where encoded string inside. Okay, here in the example given, 3 braces of a, that would repeat a 3 times, and then okay, b c 2 times. Okay, got it. So as I was mentioning, we can make use of a stack for these kind of problems. Basically, whenever we have nesting, stack would come handy. So let's create a string stack, and let's create a num stack as well. Stack of string, which will be new stack, and then stack of integer. New stack here. Okay, and what else do we need? We need a number, current number. So let's initialize it to 0. And then, okay, we do not need it as instance attributes, but we need all this here. Okay, and then let's keep iterating through each character in this string for char, current char, s dot to char array. Okay, once we have this one, okay, we know the current character. If character could be a digit, first thing. If current char is a digit, then what should we do? Then we will just try to figure out the value of that number or update the value of that number. Value of number is equal to current num multiplied by 10 plus current char minus 0 if it's a digit. Okay, what if it's not a digit? What are other chances? So in this one, if it's not a digit, then it could be open braces like this. So else if current char dot current char equal to an open braces like this, then what should I do? I should be adding if it's an open braces, that means I'm done creating the number first thing. So I'll be adding my number to the num stack dot push current num, and then I need to reset the current num value. So I will reset it to 0. After that, what should I do? After that, I need to push my string as well, like whatever the string that I had until now. Yeah, string tag stack dot push. Okay, let's hold on to this one for now. Let's hold on to this one now. What other cases are possible? Else, if another case here is, it could be an alphabet or it could be a closing braces also. So if it's a closing braces, let's consider the alphabet case scenario later. What if it's a closing braces? If it's a closing braces, then else if current char is equal to, okay, if it's a closing braces, then what we will do, we will have to get the number or k, which is the function that we applied here. Int k is equal to, take it from the numstack dot pop the value. Once we have that, let's create a string. Okay, string builder. Okay, string builder, and then okay, I will mark it as decoded. Current decoding is current decode is equal to new string builder. Basically, all I have to do is for int I is equal to 0, I less than k, plus plus, and I will be appending the string as many times as possible. Dot append. Okay, I need something to hold the current string as well. Current string. Okay, so that would be the current string. Okay, once that is done, I will current string would become equal to current decode. Okay. Okay. If that is not the case, that means it would be a plain string. If it's a plain string, then I will just add it to the, or append it to the current string. If it's just a character like A or B or anything. Now, at what point I'll just okay. So all the computations that I performed here that came into current string or the current decode or decode till now. Let's make it as decode till now, and let's add it as, okay, whatever the current string. And what about the previous computations that we added? So let's push that one here, current string dot toString. Okay, this would have all the previous computations, and after that I will initialize the, once I push it to the stack, I'm initializing the new string builder here. So until then I kept calculating the current string. and then I will have to take the same thing out of that stack, and then build on top of that. Decode till now. Okay, decode till now dot append current string. Okay, I'll keep appending it, and then decode till now would become the current string. Okay, this should be good. And then finally, I can just return current string. Wow. So yeah, let's, okay, nice. So let's look into this one once. Let me explain it slowly here. So there are 4 cases in this example itself. There are multiple ways the input characters can be. So if it's a digit, then I'm just forming this number, which is stored in this current number. All I'm doing is, okay, it was a digit 3, so that should be 3, 0 cross 10 plus 3. So current number value is 3 now, as you can see here. So the next one is open braces. So when there is open braces, I just push the current number into the num stack. I just pushed it to the num stack, and then I reset the current num value to 0. After that, current string, whatever I have, there is nothing as of now. So I will push that to the push that to the string stack. And then current string is initialized to a new variable again. So the next element is a. I will have to add it to the current string. I will append it to the current string. So I appended a to the current string. So current string became a now. Next element is closing braces. So now you can see we will perform the computation of, like we have 3 in the num stack and then current string is a. We will perform that computation and then add it to the current string. So now the current char is closing braces. K, I took it from the num stack, which is 3, and then decode till now is empty now. So, but I will keep appending to decode till now for the current string. Current string is a. So I took a 3 times, and then okay, that is done. Now I decode till now became a. I will append it to the current string, and then next element is 2. Again, we will go back to seeing the digit. Current number will become 2. And then again, next character will be open braces. At that point, I need to add my current string, whatever I have decoded till now, into the stack. And then I'll initialize the current string as a new string builder. So if you see, current string is a new string builder. And I have added the decode till now as AAA. So yeah, so now let's okay, I'm done with the 2 now. Okay, and then now again open braces. Now not so I'm decoding B now. I added B to the current string, and then current string will become BC now. Current string is BC. Now there is a closing braces, so I need to perform the computation. So in order to perform the computation, K, I took the K from the num stack, which is 2. So K value is 2. String builder decode till now. In order to decode till now, I'll take whatever is in the string stack until now. So I took that A, whatever we had computed, and then I'm decoding twice here. So BC it will be A BC. So that I'm assigning back to current string, and then we are done with all the iteration. I'm just returning the current string. Yeah, so that's what we can submit here. Yeah, let's look into the next problem now. Decode string, and now it is 3 sum. Okay, for this one, it is an extension of the 2 sum problem, but like we are asked the sum of the 3 elements to target. Given an integer array nums, return all the triplets num of I, num of j, num of k, such that I is not equal to j, I is not equal to k, and j is not equal to k, and num of I plus num of j plus num of k is equal to 0. Notice that the solution set must not contain duplicate triplets. Okay, so here in this case, I'm given the array in the same way. There are negative values also in the array. I need the output, and I just don't want one combination. I need the all the combination that can lead up to value 0. And then here you can see -1, it's not the same value, but there are there are 2 instances of -1 in this array. So that's why I'm able to get that combination here. -1, -1, 2, and -1, 0, and 1. Okay, the way I'm solving this one is, okay, first thing is I have initialized the output as as an array list, and then if nums.length is less than 3, so here we have to find out the triplets. If the total array size is less than 3, then there are no combination possible that way, so I'm just returning an empty array list. If not, I'm sorting my integer array. What is the sorting operation? Sorting operation would take n log n for an array. So I don't mind, like I'm trying to solve it in n square. I'm just sorting the array. After that here, what I'm doing is, if I is equal to 0, I less than, okay, I'm iterating through the array one by one. If nums of I is greater than 0, then break. Okay, why is this? Okay, because I'm breaking away from this loop when there is a positive integer, because we are checking if the sum of 3 elements or three numbers is 0 or not, and then I have sorted it in the increasing order. That means if I come across one positive integer, that means the next ones will be positive integers, and then only positive integers cannot make a combination to or a summation to 0. So until then, whatever the answers we got, we can just return it. That's why I'm breaking away here. And then another condition is, if I is greater than 0, and if nums of I is equal to nums of I minus 1, then just continue. If I is greater than 0, and if nums of I is equal to nums of I minus 1, then just continue. That is, I'm doing that because, let's say -1, -1, 2, this is one of the combination where -1 was selected first and -1 was selected first and then 2. Let's say there is another -1 in the mix here. Then I cannot return -1, -1, 2 again as the similar combination, because notice that the solution set must not contain any duplicate triplets. So this is the, like, that triplets can contain duplicate numbers, but the solution set must not contain duplicate triplets. That's the rule. That's why if I is greater than 0, and if nums of I is equal to nums of I minus 1, then I'm just skipping one of that. Okay, and then I'm just figuring out, I'm just trying to call toSum method for every number here. How toSum method? toSum method is same as whatever we saw in the toSum. I have a complements map, and then I'm iterating through each index or each element in the array, starting from index plus 1 in this case, and then current is equal to nums of I, and then complement is target minus nums. If complement dot contains complement, okay, if complement and how I'm coming at the complement, there's a target. How I'm coming at the target here, that you should see. So here in the toSums method, I'm passing the nums array, I'm passing I is the index, like from which index I'm considering, and then -1 star nums of I. So -1 star nums of I means basically that's the target. So here 3 elements should make up 0. That means the sum of 2 elements should be equal to negative of the other element. Like for example here, let me elaborate. Nums of I plus nums of j plus nums of k should be equal to 0. That means nums of I plus nums of j should be equal to minus of nums of k. That's where I'm deriving the value of the target here. Nums of minus 1 star nums of I, and I need to figure out the nums of j plus nums of k, which would be equivalent to minus 1 star nums of I. And I'm checking all the indexes or all the elements after this index to get that combination. So yeah, so that is and then I'll keep adding it to the output also. Okay, two sums nums. Okay, and output three sums I have added here, and output three sums is here, and then I have called two sums. Okay, how I got the output three sums? Okay, that I have created as an instance variable. I am not passing it out here, but still I have access for that one. If complements dot contains complement, then I might be doing something extra here. Dot add new array list of integer, and then here lists of a list of target star minus 1 current comma complement, list of target comma minus 1 current comma complement. Okay, because this is returning list of integer. Okay, so I'm creating a list of integer here, if the complements contains the target, and then while I plus 1 is less than nums dot length and nums of I is equal to nums of I plus 1, I plus plus. Again, to avoid the duplicate combination here, I don't need one more minus 1 2, or 2 minus 1 or anything, the same triplet or similar triplet. That's why I'm kind of incrementing the value here. If nums of I is equal to nums of I minus 1, I plus 1, then I plus plus here. So yeah, that's when I'm adding the complements as well. Complements that add current. Okay, if I don't find this one, that should be good for three sum. Let's move on to the next problem. Here, valid parenthesis. I think we had seen this one sometime. Let's look at how many problems are over. So there are 17 problems done now. So valid parenthesis. So here, it's a LeetCode easy problem 20. Valid parenthesis. Given a string S containing just characters, open braces, close braces, and open other types of braces and all. An input string is valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. Every close bracket has corresponding open bracket of the same type. Okay, so what we can do, we can use a stack, and then whenever we have open bracket, we can just push it to the close bracket, push it to the stack, and then whenever we have the close brackets, then we can just pop out of the stack and see if that is the matching matching open braces there. So I'm doing for the braces pair, I'm just creating a braces pair here. For every open braces, I'm storing the same type of the closing braces, corresponding type of the closing braces, and then I'm using a braces stack. And then if the braces pair contains, okay, if the braces pair contains the current character, that means I'm pushing it to the stack. That means basically I'm checking if the braces pair contains key, means it would be an open braces. Like if there is a closed braces, then it would return false. Okay, because I'm not checking I can't check based on the closed braces here. The keys are the open braces. So if the braces pair contains char, or else if the braces pair is open braces, then I'm just adding it to the stack. Else, if braces pair does not contain it, that means it's one type of closing braces. If braces stack is empty, okay, or if braces pair dot get braces stack dot pop, okay. So what I'm doing here is braces pair dot pop, braces stack dot pop. So I'm taking something, taking out of the stack if the first element, and then I'm checking it with the value of that particular key. let's say if the current value is that I got is this type of closing braces, then I need to see from the stack what's the first element. If the first element should be this type of opening braces. Okay, so I took out that first element from the stack, and then I'm checking if the value for that one is equivalent to the current character, then I'm not doing anything. If it is not equal, then I'm returning false. Okay, and if it is equal, then I'm not doing anything. I need to evaluate further. And then at the end, like there shouldn't be any additional open braces as well. That's why I'm just checking that braces stack is empty or not. If it is empty, then I'm returning true. Okay. Okay, valid parenthesis, reverse words in a string. Okay, the sky is blue, blue is the sky. LeetCode 151, reverse words in a string. Given an input string S, reverse the order of the words. Word is defined as a sequence of non-space characters. The words in S will be separated by at least one space. Return a string of the words in reverse order. Okay, reverse order of the space. Okay, so this is LeetCode 151, reverse words in a string. So let's see how we can do it. I think there must be a simple solution for this one. So we can split the string using string.split and then we can just reverse that in a couple of lines using the collections framework. Let's do that. Okay, so let's get the string words is equal to s dot trim. We use trim means if there are any additional characters or additional spaces that would be trimmed as well. And then let's split it based on white space. Collections dot reverse arrays dot as list words. Okay, yeah, collections dot reverse arrays dot words, and then return string dot join all those words with nothing. Okay, let's see, first with the single space. Okay, I'm joining all those words and returning it. Okay, so here in the example 3, there are multiple spaces. That's when it is failing. Okay, I thought trim could handle it. Trim might handle only the leading and the trailing spaces, not the other way around. So it handled that leading and trailing spaces case, but there are multiple spaces in this one. So I think it can be used by white spaces regex here. So let's try that one. Okay, that one works. Let's submit it. Okay, so we got it. I think this should be good. Otherwise, let's see what all solution can be present. Often, okay, int left is equal to 0, right is equal to, okay. Remove the leading zeros, okay, remove the trailing zeros. So basically, whatever the trim performed, and then DQ, array DQ, okay, string builder word, push word by word in front of the DQ. While left is less than right, char c is equal to s dot caret left, okay. If word dot length not equal to 0 and c is equal to, and if the character is equal to space, then push it to the stack or a queue, okay. And word dot set length or 0, and then make the word, okay, reset the word. Otherwise keep appending character by character to that word. Okay, makes sense. And then do the string join the same way. That works. So let's look into the next problem, which is move zeros. Okay, given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Note that you must do this in place without making a copy of the array. Okay. So, okay. So non-zero elements has to be moved and rest of them we have to keep it as it is. So here, okay, index is 0 and then we are iterating through the elements one by one in the array. If nums of I not equal to 0, then nums of index plus plus is equal to nums of I. Okay. Okay, all I'm doing here is as and when I come across a non-zero, I'm moving it to the index which is initialized to 0. And then I'm incrementing this index as well. So let's see, I'm iterating through this one. I came across 0, I won't do anything. I came across 1 and my index is pointing to 0 as of now. I'll move this 1 to the 0th index. Okay, and then I came across 0, I won't do anything. And then I incremented the index to point to this one. And then I came across this one 3, which is a non-zero, and then I added it to the index position. And then I move the index to +1, and then 12, which is non-zero, I move to the index. And then after iterating through all the elements, once I exhaust it, I will set the remaining elements to 0. This is clean. Yeah, that makes sense. So these were a lot of easier problems here. Let's look into implementing try. So that is like I always consider try as somewhat similar to a non-binary tree. Like binary tree will have only 2 children, so try can have multiple children. Somewhere like graph but without cycles. So let's look into this approach. Like we have try constructor and then we have insert method, search methods, and everything. Let's try to implement it. In order to implement that, we need to have a node as well defined, or have they defined it already? No, I don't see anything defined for node. So let's define a node for the try. So class try node is equal to, or so this will have a list of try nodes called children, and a new that will be of try node type, and that would have a length of 26 in order to just fit the alphabets here. And then boolean is end. So if that child is the end of the string or not, basically that's what we are determining there. And then I need to determine the root. So try node root and then here root is equal to new try node. Okay, when we need to insert a new word into the try data structure, then we go character by character. How? Starting from the root is equal to, or node is equal to root, and then for I'll start iterating character by character of that word dot to char array. Okay, and then int char index is equal to c minus a. Okay, and then if node dot children of index char index is equal to null. I mean, if that doesn't contain a try node, I mean, if that doesn't have any children in that node, then node dot children of char index is equal to new try node. I'm just defining a new try node here. And what I'll do once I'm at the end of this one, in order to continue the loop, I need to do node is equal to node dot children at char index. I'll keep adding it further that way. And then once I add all the elements or all the characters, that means that's the end of the word. So node dot is end, I will make it as true at that point. Until then, it would be false for all the other nodes. And then let's see starts with or before starts with search prefix. So here these two has a common logic. For example, okay, search and returns true if the string words is in the try, that is was inserted before, and if the string word is in the try, if it was inserted before, and returns false otherwise. Starts with returns true if there is a previously inserted string word that has a prefix, okay, and false otherwise. Okay, let's see. For starts with, we need to do try node is equal to root. Let's start with that, and then let's keep iterating through each character by character in the same way here. Okay, and then next thing is, okay, char index is this one. If node the children of is equal to null, then I won't be inserting a empty element, but I'll just return null or false. Then I'll just return false. Otherwise, I need to do node is equal to node dot children of index. Okay, and at the end, like, okay, I come across these things, and then until then, if I don't return false, that means I can return true. So for the search also, it should follow the same logic, but with a minor difference. Let's see. I keep started from the node, and then I keep iterating it, and then at the end I'll just check whatever the node remaining, if node dot is end is true, then it would be an absolute word than just starts with. Let's check this one. Oh, this is prefix. Okay. Wow. This works well. So here in the search and the start with, there is a lot of common code here. So what we can do here is we can just get this one, and then try node is equal to search prefix of prefix, and then I will implement the search prefix, which should return a try node type, and then string prefix. Okay, have the try node, and then return node here, and then here, rather than returning false, I'll just return null. Okay, so this should be the deal here. And then if here, when would I return true? If node not equal to null, then I would return true. So if node not equal to null, then I'm returning true. And in this case, one thing is node not equal to null, and node dot isEnd is true as well. And I will replace that also with the statements, and instead of prefix, I'm passing a word here. Okay, so this one works. Yeah, that looks good to me. So we have the implement try also. So all I'm doing is like I'm traversing in a tree. I'm traversing with the try here, and binary tree will have only 2 children, but a try will have kind of like an array of children with 26 characters in this case, because we are trying to store a string there. So let me know if any of you have any questions. I'll just okay, I see Saddam has some messages. Let me see that. How about going from end to start, and we push okay, close to the stack until we found opening. Okay, that was for a different problem. We use stack, and if we found number, we empty the stack and update the output string. Yeah, exactly. Is try is type of binary tree, or what is different? Okay, learn about tree first and try first, and come back to this problem again. Yeah, this is basically implementing a try. This is the try as basic as it can get. Try is not a, I mean, binary tree means basically a tree with 2 children. Here we can see the node, how the way we have defined the node is like a tree with 26 children. Every node can have 26 children, basically 26 different characters, and then we have a boolean signifying whether it is the end of the word or not. So here I initialize the root node with the try node type, and then when I want to insert a word, like for example, um, let's look into the debugger here. That should give an idea, but yeah, we have a node here. So let's see. Okay, we are trying to insert apple as the word here, and then okay, we have the node this is the root node. Basically, root node has like children with all the empty array, or the entire empty array, like all the 26 children are null here, because I haven't added any word. All the children are null. Now since I want to add a here, first letter is a, right, like in apple. So this one would become a new try node, and then I'll assign a value for that, and that will subsequently have 26 children again. Let's see how that one looks like. So current char is our char index is 0. Char index is 0. So I need to check the element at our children at 0th index, and I check that it is null, 0th index. So I will be adding the 0th index element child 0th index children with a new try node. Now you will see this will be a new try node. So now the children like okay, we came out of this one. Okay, node dot children of char index, and then is index false. Okay, but why did this node got decomposed or compressed? No idea. Okay, let's come back. Okay, and node became node.children again. Now I need to add p into that one. So to add p, I won't do anything to 0th index or anything. So p's index is basically, we can see char index is 15. P is the 15th character. So I will be modifying the 15th index here, whatever the 15th index in that node, and then I'm assigning the node to the 15th index, and I will add p again. So one more p, that is the 15th index, I will add that again, and we can see that, and we need to add l. L will be 11th index, I am adding that later. So I keep adding that one. So after adding all that, I set that node.isEnd. Okay, that's the end of the word. I marked it as true. Whenever I come across app, like if there is a, like if I want to add a word called app in future, so a is already inserted there, p is already inserted, and one more p is also inserted, but there is no flag signifying that app is a word. Then what I'll do is I'll set node.isWord, like I'll keep this one, will keep iterating. If node is not null, it won't bother creating a new try node. Basically I will just traverse through that node, and then at the end I am just signifying that app also is a word, not just apple. So yeah, and then if we search for some specific word, the same iteration pattern follows. So yeah, so that should be it. It is easy if we understand tree. Try is like a sub concept within tree. That should be it. So that's the end of the session. Please write if you have any feedback or suggestions to me. And one more announcement here. So I created a WhatsApp channel. Like there, I'll be posting a lot of communication part, and I will use that to publish anything that I want to let the group know beforehand, and I'll have my phone handy to publish there as opposed to in this one. So this is the link. Okay. Okay, I'll share the link for that WhatsApp channel group um, in somewhere in the description here, description of the video when I post it. Please keep please stay tuned in that WhatsApp group for any information that I want to post. And yeah, you're always welcome to provide me any feedback, and thank you for your time. And I will try to help as much as possible. And trust me, this has been helping me. I started interviewing as well, and this process of basically live streaming my preparation here has been helping me a great deal. So if you want someone to keep you accountable, then I'm there. Just post it in the comments what you are trying to accomplish and what you are trying to get out of this one. I'll try to help as much as possible in your learning journey. So until next time, let's keep learning and keep improving. See you guys. Bye bye.